Here we go. So we're gonna keep on practical stuff. Okay, I think we can talk about the theoretical exam from the last year. But I think because you guys do show a sense of, okay, we want to do this, we want to learn. Maybe there's bumps and issues in the beginning, whatever language things can happen. But I actually think the most decent thing would be to actually do a theoretical exam. You get some questions, you write your answers, kind of stimulate you to absorb this material and all the rest. Rather than be like, yeah, whatever you like, just write an essay or something. I mean, you guys are here with your own motivation, you've come from far away, so I think you definitely have something, to do, and it's of your own desire, I imagine. So we'll talk about this, and obviously I'm interested in your opinions when you want this to happen. Obviously you cannot get the mark before the end of the semester, so we can push it until January, I think, or something like this. But you can always, we can do it earlier as well. And I will send you the playlist, which is audio signal processing, and the SuperCollider playlist. And actually you have years worth of material, lectures there, things that may improve your understanding on top of the books. So it's the kind of thing you really need to, I think tighten your belt, is that the expression, kind of, okay, let's do this, let's be serious about this. And I know some of you will do this as well, so I would like to see that happen, and hopefully the ones will pull along the others and actually get some really good work into this material, because it is your foundation of electronic sound. The better you understand it, the better you understand everything you do later on. So we'll continue talking about that, and then today what I imagine is let's crack on with interesting stuff. So more so than showing you, interesting patches, ready-made patches, I'm gonna try to and make sure that I show you how you can build from nothing rather than, adjust things. I guess you've been through this stage already. And the first important thing, the first thing that I want to ask you, shall we just revise a bit from yesterday? Just one main question remains. I hope it doesn't remain, but it is, what determines the distance of the sidebands?
The frequency of the modulator.
Exactly. Modulator frequency, that's it. Modulator frequency determines the distance of the sidebands. Great. So I'm really happy to hear that. Okay, it's getting there. It's worth knowing. I'm not going to go now into the actual signal processing implementation, but there is such thing as single sideband modulation. So what we've done and we've looked at is a case where you have two sidebands that slide away from each other. I'll flash these terms using quadrature processing, using complex signals, which is signals made up of X and Y component, so to speak, two-dimensional signals. Using those, we can actually create a single sideband modulation, which means that I'm duplicating the given spectrum, but only in one direction. I'm not getting what you've been seeing yesterday, that they slide apart, but it just climbs up or climbs down. And that is your frequency shifter. Okay, and it's crucial, I think, at this stage. Hopefully we'll get the time to dig into the details. But the difference between frequency shifting and pitch shifting, are you aware of this? I might have mentioned it last year. The difference is that frequency shifting literally shifts, which means that every spectral component is shifted by an exact amount in hertz. So how you can recognize them typically is that the frequency shifter will have the shift parameter and the unit is hertz. So it means if I have a 100 hertz component and I shift by 50 hertz, it's going to be 150. But the same thing will happen to a 1000 hertz component. It will be shifted by 50, yielding 1050 hertz. Okay, so if I say this already, you might get the sense. Okay, well, actually a distance, so to speak, musical distance, between 100 and 150 is much larger. It's actually a third, right? Sorry, a fifth interval, right? It's much larger than the distance between 1000 and 1050. So actually frequency shifter does not preserve harmonic relationship between the components, right? So what actually happens is as you use a frequency shifter to shift things up, you could say that things come closer together as you shift them up, right? And vice versa, if you shift them down, I guess I'm saying this right, they come further apart. Now the pitch shifter is a different ball game, and that pitch shifter preserves the harmonic relationship of the harmonic components, and you can recognize it because the parameter is called ratio, and it already tells you, so it's not a fixed shift in hertz, it is a fixed multiplier. And you remember now, hopefully I've been talking about fixed multipliers already. Okay? So just you know that this modulation business, this sideband business, shifting business actually goes deeper and deeper. We're just scratching the surface here. Okay, I won't go very deep into this now. What I prefer to do is actually get you a bit warmed up with our little patching and stuff like this. So let's talk a bit about, you've seen the ramp, line.kr. You have the other envelopes as well. They work in a similar fashion. You're probably aware of the fact that they can be re-triggered. Okay, so we didn't really deal with this much, but if you look at the help file, I hope you are friendly with looking up help files. And this one cannot be re-triggered, it seems. Start, end, duration, output, yes, and done action. Are you guys aware of the done actions? Maybe Andras was talking about this. So you might, I mean, the strategy that I'm employing here is disregarding the relish, the side dish, and I'm just giving you the meat, or if you're a vegetarian, the veg. There's a lot of things to take care of if you want to build a solid functioning SuperCollider program that runs something, you know, reliably. What we are actually doing here is just focusing on the sound synthesis part. So I'm kind of excluding these things which are not within the curly brackets .play. So actually all I will be doing with you guys is just this bit. And then probably you had some info on, you know, how you can start these synths, restart them, and how you can stop them. So done action has everything to do with stopping the synth. So when the ramp runs out and so forth. So line that cannot be restarted. ADSR is, so the way envelopes work, if I remember correctly, is that we have the env class, which actually specifies the type of envelope. You can specify it as a list of levels, times, and curvatures as well. And here is the, so that's a definition of the envelope, which happens out of real time. Okay, it needs some extra calculation. It does not need calculation sample by sample. Because actually most of the things we're doing here, most of the UGens, they do calculation sample by sample. We do have IR. So we have AR, you're aware what this is? It's audio rate. We have KR, which is control rate, which means that the KR runs less frequently, saving some CPU. We do have IR, which is initiation rate, which is supposed to run only once when the thing starts. And we also have the demand rate, by the way. So you can actually set up a processing chain whereby calculations happen on demand. So it doesn't have to be a regular pulse or regular period like that. Okay, so here what you see then is that the env defines the envelope that you're going to use, it does not have AR or KR because it's not running in real time, but it is embedded by the env-gen, and that is the generator that uses the definition and actually runs in a control rate in this instance. And then the env-gen has the first parameter being the actual envelope that you typically define using this convenience class. And then you have the gate parameter. So the gate parameter will be the trigger. So this is an envelope that you can re-trigger. And here it is re-triggered with an impulse generator every 3 times per second. Okay, so it's 3 hertz, this impulse generator. Okay, so that's the general structure of the envelopes. And then here what you can find is different ways of defining it. Okay, so the basic envelope needs these lists. You can use these curves and so on and so forth. It can get a bit more complex. And then you have some standard shapes. Okay, so here we have a linear envelope, attack, sustain, release. Can anyone tell me what is the difference, what is the characteristic of the ADSR in terms of triggering it? In other words, what is the difference in terms of triggering an ASR? This linen is an attack, sustain, release envelope, and the ADSR.
So if we have a MIDI keyboard, if we press the button or the key, we trigger the attack. Then if we hold it, it stays at some point. This is sustain.
Yes.
Then we release it, and it
exactly right. So what happens is it needs 2 triggers. It has an attack trigger, it has a release trigger. Okay, so in this case, this ASR does not have it. Now you see again, think it through. You see this env linen does not have a gate parameter. Why not? Because it is just defining the envelope. It's not running it. Okay, so this is the thing to figure, that we are doing this separately. And once we get to the gate parameter, well, I won't, let's just mention these. There's different shapes, different parameters of envelopes that you may want to create. You can also create a oscillator using this, right? Do remember, and this is one of the things that we're going to look into today in practice, that if you have a repeating waveform, it can only contain integer multiple harmonics. Okay, so no matter how beautiful your waveform is, it's very important to say this, I believe, because we still have the remnant of the ancient paradigm. I mean, in sound synthesis, 100 years is about old as it gets. The paradigm whereby, I mean, it was just a fascination of the scientists in the domain, that they have finally plotted the waveform of a clarinet. And for some decades, it was believed that if you have the waveform of the clarinet, you know everything about it, right? But that's not the case. That's not the case, not even close, right? So that's what I'm, kind of working against, just so you understand, because there's also some fascination with sonification. And, I might say, well, I'm very proud of the shape of my nose, so I'm going to take my profile and I'm going to make it a waveform, and this is going to sonify my face. Actually, in this case, it probably did. That's probably it as well, as far as the aesthetic goes. So I'm always trying to work against the stuff that might be kind of assumed from, novice, kind of just some basic activity in the domain from gathering the, popular beliefs and such. Okay, so that's that. And then let's try to do an exercise with an envelope, okay? To start with. So I'm going to draw it for you and ask you to code it. Okay, so what do we do? Well, in order to do this, let's dig slightly deeper. I guess you're not horribly excited by square waves and sawtooth waves already. You might be, who knows? It might come back. But one of the really cool things in SuperCollider are the chaotic oscillators. So I'm going to spend some time, I think I did a bit last year, right? I was talking about chaotic oscillators. It's one of my favorite topics. I typically don't skip it. So if you browse the help files, you go to UGens, and here you have generators. So the generators are the bits that are kind of oscillatory, things that generate a signal from a few parameters typically. And here we have the chaotic, deterministic, granular, physical models, single value, stochastic. Stochastic means random, related, or based. Okay, so let's check a few chaotic ones, and there's 26 of them, so quite a few. And I'll get to some explanation at some point, but let's just get this example file. I guess you understand that help files have runnable examples like that. How does this one sound? Okay, so this is a Hannon attractor, and N typically stands for non-interpolated. In SuperCollider, you will see the L letter, capital L, at the end of things for linear interpolation. You will see the C for cubic interpolation. Typically, those are the options that you have. By the way, there's some really interesting ones like spline interpolation. In fact, interpolation is a fascinating thing, maybe for you because of the math. When I was a student, I was very interested in this. And I was like, okay, so there is cubic interpolation, so why is there no quadratic interpolation? And the one that I came up with could explode, which is even more fun, because, it's weird. So kind of generating values between values, so to speak, which is interpolation, or extrapolation, which is continuing a signal, is a kind of a low-level audio interest that I hope sparks your imagination. So Hannon N, well, first of all, let's check the parameters. Okay, so methods are frequency, iteration frequency in hertz. Okay, so typically what you get is that these UGens do not run every sample. They run on a subset of samples. And here you have a number in frequency, a number in hertz that determines it. And here you see the IR. It is initiation rate. So this is actually a UGen, which will run only once when you start the synth. It will query the sample rate from the server, and it will inject the number there. What do you think? Why is this useful in this case? Why is it useful to make the iteration frequency dependent on the sampling frequency? Well, you see, it has to do with the pitch of the sound, right? So because if you have a relationship, if you have a fixed period for running this UGen and you increase the sampling frequency, you will increase the pitch of the UGen with it, right? So this actually makes sure that it is independent of the sampling frequency. May you run your patch at a different sampling frequency. Because otherwise you'll be surprised. It's like, okay, well, suddenly it sounds very different from yesterday, and it shouldn't. And you understand that all the normal UGens, all the oscillators, they will run the frequency that you want independent of the sample rate. So they kind of have this internally. And the nice thing about SuperCollider is that it's been designed with efficiency in mind. So actually, it's never checking whether you are sane or whether you've done the right thing. It's always doing the minimal work. There is no work behind the scenes, which is actually really interesting because it's in contrast with what we expect from technology these days. Like when the kids start swiping all over the place and, we start to treat tech as if it was perfectly designed to work on our cognitive level, you know, with the symbols, with the way we think. And when it doesn't do something we expect it to do, then we are surprised. Now, if you, you know, understand how it was back in the day, you never expected the computer to do the thing you wanted. You expected to be able to learn how to get it to do things for you, right? So it was always a sense of, okay, I am the brain and the computer is a tool that I can or cannot use or learn how to use. And these days, unfortunately, I say, what's happening is that we have the idea, well, that's the brain, and I'm just a human, I'm a playful, improvisative, whoever I am. But we kind of expect the intelligence to come from it and the ability to serve me rather than my ability to use it. So that's also part of the way of thinking that I like to spread in terms of working at this level with sound synthesis, that you really consider it you who are the brain, and this is just a very powerful tool, right? So it won't do things for you that you don't ask it to do. And it's been programmed like this largely, that it doesn't do things that you don't ask it to do. Okay, now other than that, we have A, equation variable, B, equation variable, initial value of x, and second value of x. Okay, so in order to understand this, I'm going to say a few things about becoming theoretical again, but never mind. Few things about chaotic orbits, just so you get a better idea of what you may expect. Okay, so technically it's called nonlinear dynamics. If you really want to dig into this, that's the term to look up. And in physics, well, it describes a lot of things. I mean, it models probably. But one of the things that's really a good example is turbulence. Okay, so if you see turbulence, where do you see turbulence? You see it in the pond, well, I mean in a little river, you see it, you know, in the airplane, things get turbulent. So it is essentially something we observe as pattern, but it is not a geometric pattern, and it is not predictable. Right? So that's our doorway into chaos, if you think about turbulence. And the interesting thing is that chaos can be produced with a strictly deterministic algorithm. Right? So when you say, well, I want something random, you take random very often in this context, right? Now, actually, a digital implementation of a random algorithm is a chaotic algorithm. And the way we approach chaotic algorithms is by looking at their orbits. Okay, so the difference is that if I have an equation, if I have a function, let's take the x squared function, we've looked at it already, I have the parabola. The way I approach it, the way I look at it, is by saying I'm going to take all the possible input values along the x-axis, and then on the y-axis, I'm going to output the value of that input, coming out based on that input. So what you have in this type of approach is the assumption, first of all, that every time you hit it with the same value, it will give you the same output, right? So there is only one dot that is related to a single input value. There is no two dots, right? Now, in orbits, in chaotic algorithms, this is not the case. We can also plot them on the XY coordinate system, but we plot the orbit. So we plot how it evolves in time. Because the most crucial thing about nonlinear dynamics is that we use recursion, which is essentially feedback, in order to get it going. So what happens is that when you have an equation, and here the equation is, normally they state what the equation, this is my equation of Hannon attractor. And what it says, first of all, well, in this case you have only y, and it's only x's. Sometimes you will have y's and x's combined, in which case x is the input value, and y is the output value. So you will find definition of recursive algorithms in terms of y n equals x n something, which means the current output yn, n is the kind of index, equals some function of the current input value, which is the xn. And then you would typically get xn minus 1 as well. So you can say that the current output value depends on the current input value and the previous input value as well. Right? And actually, you see what happens then is that you're actually running it in feedback. So this is a slightly different convention. Here you have the future value, so to speak, right? So it says that not the future, one after the next value will be a function of the next value and the current value. So that shouldn't confuse you. It's still the three values. It's still the output. So this is the output, and this is the previous input, and this is the one before the previous input. Okay? Now, also what you will find then is that this depends on two previous outputs, but actually it can also depend previous inputs. It can also depend on the previous output, which will be the feedback loop. So just to, I don't want to spend, this is not the main topic that I want to dig into. Hopefully your imagination is getting excited and you can dig into this further. But the main concepts that we really need in order to approach this meaningfully is to understand some basic facts about chaotic oscillators. And this effect, the fact that you see I have two initial values, should now slot into place in terms of I cannot run a chaotic algorithm without having a seed. We also call it a seed or the starting initial value. So you probably know that even if you take a very basic random generator in MaxMSP or otherwise, it will have the seed parameter, which you don't need to use necessarily. The reason is that this algorithm is defined recursively, so it has to have previous values in order to be able to give you the next values. You can say they are zeros, but very often the zeros will not yield an output. So actually, a chaotic algorithm, the evolution of it, the orbit, will depend on the starting values as well. But it will depend on them statically. Okay, so once you start it, when you start this, you can play around with changing these. Maybe you get a different result, but it doesn't make sense to modulate these or to, ramp them or anything. They're just initial values, okay? Now, other than that, here we have two equation variables. Now, there is not much more information. For you to actually fully understand the Hannon attractor and its application in sound synthesis, I would say, take a master's thesis with this topic and let's do it. These are really interesting, really deep-going, complex things. One of the things that is certain that you can expect from each one of these is that there's three types of orbit. One is a stable orbit. So such an algorithm can start giving you a fixed value and give you a fixed value forever. Okay? You can also get asymptotic or attractor type orbit, which is still in the category of the fixed orbits because it's a monotonous orbit like that. The next one up is the oscillatory orbit. So you can get these algorithms to go up and down. You can get them to go up, middle, down, middle, up, middle, down, middle. You can get a 3-point cycle. You can get a 4-point cycle. You can get a 5-point cycle. You can get any point cycle from most of these algorithms if you study them. Okay? So those are the oscillatory orbits. And then you get the chaotic orbits, which for us essentially amount to this noisy signal, right? Because turbulence is noise, right? So when I play the flute, actually the jet stream becomes turbulent on the edge of the mouthpiece. And that's why the tone of the flute is really noisy. You know, there's a lot of air sound, so to speak, the wind sound, right? The wind is also the sound of turbulence, right? So the turbulence is an approach to noise. And the reason why these algorithms are so cool, because you actually have the opportunity to go from nothing, stable orbit, oscillatory orbit, into chaos, and kind of move between these things. Okay? So, those are the general things. Now, few more things to know is that these algorithms can blow up. So they can, what we call, escape to infinity. This is a term you will encounter if you dig up this literature. And in fact, you might know of things like, what you might know of, fractals. You actually have escape time fractals. I won't go into this because we are dealing with orbits. Okay, let's stick to the orbits. So they can explode. So it can be that you make a set of parameters exploring this generator and it doesn't make a sound. It can be that it makes sound for 1 second and then it stops making a sound. So, word of warning, don't use headphones with this stuff, especially not loud. You can use them if you're soft. If you really like the sound and want to hear it, push it, but then push it back. When you start changing values, things can get really nasty. You can blow up equipment, you can harm your hearing apparatus. Don't want to do that. So be very careful. Okay, but you know, that amount of weirdness is probably the amount of interest, at least for me, definitely is. Okay, so let's analyze this. So what do we have? So we have a sample rate related frequency. And then we have two LF noise generators, which are low frequency noise generators. Here, I mean, this is a kind of, you might say, weird thing, because actually here the N determines the kind of interpolation. If there is no interpolation, it becomes a staircase type jumping between values. But actually with the LF noises, you have 0, 1, and 2. And it could have been NLC as well, because 0 is no interpolation, 1 is linear interpolation, and 2 is cubic interpolation. So this gives you a noise signal that will be curved somewhat. You get a new value every second, right? So this is the frequency. And then, let me make sure I'm saying the right thing. The other two arguments here are only multiplier and adder. So this is back to our range conversion stuff. So it allows you to specify the range. But I'm pretty sure if you don't use this and do dot range, it will simplify your life, because then you see the boundaries. You specify the boundaries rather than the multiplier and the adder. Now you see, that is actually already the reason why I've spent much time with multiplication. Because you see, if you encounter this and you say, well, that's just a multiplier on top of this generator, okay, it's the volume. You see? Because that's typically what it is. If it's used as a modulator of a parameter, then it's a range thing. If it is audio rate signal, which it could be, I could easily put my microphone signal just instead of this number, then what? You see, so that's the reason why I'm trying to really build this foundation to be solid, because then you immediately know, oh my God, the multiplier can do so much for me. You know, that's the point here. Cool, so those are the two noise generators, and that's the kind of sound we get. Okay, so what I will propose, well, let me first just check. I'm really curious. I suppose that I can drop this in real time. So let's try. I will drop this from 10,000 to 5 in 50 seconds. Does that actually, it's easier if I watch my... I think it's happening. You hear it happening. It's dropping the frequency of the calculations. Now, you hear these things that we've heard yesterday as well. What were they? AA. Aliasing artifacts. It's a very neat term. If you ever go for an interview, you know, like that, you say aliasing artifacts, you get the job. You know. Why?
Not filter.
Well, actually, aliasing, remember that, can never be cured by filtering. So, you know, once it's aliased, once you have a sharp corner that is too sharp, so to speak, for the sampling frequency, you cannot actually filter. I mean, you can filter, but you're losing high frequency content, which was supposedly valuable as well. So the actual answer is, the reason why you get aliasing is because it's non-design, right? It's a chaotic algorithm taken from a totally different domain, here in sound synthesis, and it will produce really sharp edges that will be aliasing. Okay? Now, I didn't tell you, but there is a really good way of mitigating against aliasing. So we've discussed how we produce band-limited oscillators, non-aliasing oscillators, by adding sine waves. Unfortunately, nothing more clever. There's some interesting papers how you can optimize this, but it's, you know, it doesn't really change the fact, so to speak. But actually, the way you can avoid aliasing is oversampling. Okay, so oversampling is a technique whereby internally you increase the sampling rate significantly. In fact, I can tell you one of my experiments that I was really surprised by back in the day, if I remember the numbers right, with oversampling, is that when I modulate the delay line with the sound itself. Maybe actually that's one of the things we might build as well, but let me just try to sketch it for you so you understand what I'm saying. So I have a delay line. Let me just borrow some of this as well. Typically, a delay line has two main parameters. Can anyone guess? We also have non-interpolated linear cubic interpolation. And the two parameters it typically has are, just as a filter, it typically has an input. And the other one is? No, it's not an oscillator, it's a delay line. So the other parameter will be? Time, delay time. Okay? So what happened in my little experiment is that I had, well, I'll just call it audio signal. And what I've done, I'm not sure how well it will show on this graphing solution, it was this, right? So I'll just put a scaling factor there. Or no, actually I should put, what should I put there? Because what happens if you create a negative delay time? It's one of my favorite jokes. You get a Nobel Prize because you've traveled in time. You cannot produce a negative delay time. So actually a good thing to do would be, in math, absolute value. Okay, so if I take the absolute value of my audio signal, I'm making sure that negative values become positive, and then I can safely input it into the delay line. And actually, what I would also value quite a bit is a scaling factor. Okay, you will hear me use this term, another winner for interviewing for cool jobs. Scaling factor, which allows me to determine the amount that the audio will influence the delay line, right? Because you always think about the ranges, right? So if this is an audio signal, the range is -1 to +1. After the absolute value, the range is 0 to 1. And then I have a multiplier, because actually depends on the implementation of the delay line. Typically it would be seconds. So actually going up to 1 second is quite a lot. So I might want to decrease or I might want to increase. So that's my control of the amount of effect. Really interesting question. What do you expect from this effect? What happens if I change the delay time as it runs? I mean, other than the obvious delay time being changed, there is a very crucial phenomenon. Do you guys know? The pitch will change. Yeah. So actually, the way to remember this, hopefully, is by linking the delay line to spatial distance, right? Because if I am certain distance away from you guys, it means that there is time necessary for the wavefront to travel. So there is a delay between us. So delay between us is less than between the two of us because you're farther away. Now, these are such small differences that we don't really notice. We feel like it's instantaneous. We instantaneously hear our environment, although it is not the case. So, Doppler effect, you probably know, has everything to do with an object approaching and departing away from me. So I have a continuous decrease of delay time, and then I have a continuous increase of the delay time. And what happens is that my perception of the sound that the moving object emits will be different from what the object emits. Okay? So you can always remember, so you know that if the delay time is shortening, decreasing, I get the pitch shift up. Because it goes, right? And as soon as it starts departing, as soon as it comes to the closest point, hopefully not at me, right? Because then, then there is no more sound. So as soon as it starts departing, increasing distance, then I get a low pitch shift. Right? Okay, so far so good. This means that if I put a triangle modulation on a delay time, triangle wave to modulate the delay time, what happens? How will the pitch shift graph look like? It will be a square wave. Because if I have a linear decrease in delay time, I have a fixed pitch shift. So when the triangle wave is dropping, decreasing delay time, object approaching, I have a pitch shift up or down? Up. So I can describe the pitch shift with a flat line, which is positive, right? As soon as the triangle starts running up, it means that the object is departing. It means that it's pitch shifting down. So I can describe it with a low fixed value. So actually, if I have a triangle in the modulation time, I will get a square wave to describe the pitch shift. Okay, that's the relationship. Which means that if I want a fixed pitch shift, I need a linear increment or decrease of the delay time. And that's one of the pitch shift designs. Maybe we'll come to the designs of pitch shift. So, what does this mean for this example? I have an audio signal. Well, what does the audio? Is it a triangle wave? No. What is it? Well, it's a lot of goings up and down, sometimes smaller dynamics, sometimes larger, sometimes low frequency, sometimes high frequency. So what do you expect this effect to do? Well, you expect it to do some kind of pitch shifting, because you see, I will never perceive a delay unless there is a reference. Right? So that's why you don't perceive the delay of my voice, because you don't have the reference of the original timing. You just get the delay, so that's fine. That's the only thing you have. So I will not perceive a delay from this effect, because I'm not playing the reference. I don't know what would have been the original. I will get some kind of pitch shifting. What can I say about this pitch shifting? If the dynamic is high, if the signal is loud, then I will get more pitch shifting. If the signal is soft, I will get less pitch shifting. Make sense? How about the direction of the pitch shift? Is it up or down? Stupid question. It's both, right? So you remember the triangle wave, right? So whenever my waveform goes up, it will pitch shift. When it goes down, pitch shift the other way. And as you imagine the audio signal, it has a lot of ups and downs. So actually you get a really dense mishmash of pitch shifting going up and down. You're kind of boiling the signal. Maybe that's a good term. Okay? Very interesting experimental thing to try. Now, I was stunned by the fact that if you run this effect at 128 times oversampling, 128 times, which means that instead of 44,000 per second, you get, what am I saying, 4 million or 44 million? 4 million. 4 million, 100 times more samples per second internally. So the original audio is not more detailed, you just interpolate. There is an audible difference between 128 oversampling and 256 oversampling for this effect. You know, just from my basic understanding of signal processing back then, I was like, well, let's just try it. Of course, it won't do anything. And I was like, wow, it does. You get a more dense, more finesse, more fine, more detailed thing coming out of it. So actually, oversampling is a really interesting one. It's a kind of an advanced technique. You don't really get to use it very frequently, but you know, most of the expensive effects are hidden, so to speak. You don't know what they're doing. My suspicion is that in some cases they're using oversampling, and this is a kind of a off-piste weird thing to think about. But actually, what it's very useful for is anti-aliasing, especially for distortion algorithms, right? So this is something you can do and is done. If you have digital distortion, you understand distortion will produce harmonics, you will get aliasing in most cases. So if you do oversampling on this, then the distortion will be much cleaner. It will sound much less digital, much less of those, well, actually you've heard it here as well, those sharp high frequencies that kind of just, you know, I mean, hail sharp digital high frequencies. I have no issue with that, you know, but it's just our understanding of the tools, what we can do, what we can't do. So actually one of the things to do here would be oversampling. You know, if I would oversample this significantly, that would help it. It's not a very straightforward technique. It can be done in SuperCollider. If you're really into this, go for it, you know. I will value it a lot, but I won't go into this now. Okay, so I'm just thinking, did we kind of wrap this up? We have any questions about chaotic oscillators in general? I mean, actually, one of the things, if I make this a cubic interpolation, it will probably be a bit cleaner. Oh, interesting, we get this. Whatever. Okay, so what I'll try let's try an exercise, okay, at this stage. So I've introduced the envelopes and the chaotic generators. So let's do something with this. I will call this some chaotic thing, because it will be curious that everyone picks a different one, and then we can see what happens. So some chaotic thing, as you see, typically has some parameters coming in, and they're typically labeled X, Y, and nothing more, because it's really difficult to describe these. They behave in different ways. They're all intertwined. There's just no real good description for these. So how do we run this? Well, let's start to build larger patches already then. So first of all, I will just make the sketch without giving you the parameters. Okay, because let's hear how interesting and experimental this can get. But I will stipulate, just to help you, all the generators that you will need. Okay, so you will need an envelope, and you will need an envelope generator to produce an envelope for one of the parameters here. Let's call this the X, or AB it was, yeah? And I will ask you to produce 2 envelopes for 2 chaotic parameters. In terms of the ranges, some of the description there might be helpful once you pick your chaotic generator. Be careful. You know, it's likely that it will start blowing up and you have to fiddle before you get a sound. So no, you can make sure that the range is 0.5 to 0.9. Maybe that's the safest range. And if that is not working, then take 1.1 to 1.3. 1 is always a funny point to cross, as you may discover. By all means, try. 0 is a very tricky point to cross. And the others are kind of, and obviously if you go really large at some point, you're also at risk of blowing it up. Which is obviously not the explosion sound, unfortunately. It's just like, it doesn't make a sound. That's the blow up. Okay, and then what I will ask you to do as well is produce, so let's make this percussive sound, and produce the percussive character additionally by using an amplitude envelope as well. Okay, so I didn't specify the type of envelope, I didn't specify the chaotic generator, you fill it in. But this is the structure I'm looking at. And just to kind of give it context, the interesting thing is, for example, that, well, let me just say one more thing about these orbits, right? So I kind of put them in order, but I didn't say the punchline, which is the growth factor. Okay, so actually, let me just rewind just a bit and tell you a bit about evolutionary biology, where we also have nonlinear dynamics. And the case is that you have certain species, typically mosquitoes, and I don't know, small rovar, what is it in English? I forget the term now. Mosquito-type beings. And what happens is that you will have certain situations where their number is stable year by year. You will have situations where the number oscillates. 1 year a lot, the other word very little. And next year again a lot, again very little. And it's something that you can track as a regularity. And then you will also have situations when it's unpredictable. And these 3 types of orbits of chaotic nonlinear dynamics have everything to do with the growth factor. So typically for biological populations, the growth factor is the availability of food and the willingness to multiply. You know, some species more, other species less. So typically what happens that in the environment there is a limitation. And typically the limitation inverts or throws back the population. So in this context, I will always call it an inverting nonlinearity. It can actually be linear as long as it's inverting, by the way, but let's not dig too deep. So what happens is that, for example, in environment, there would be a predator. So what happens if I have a ton of mosquitoes because there is food and they want to multiply, then for the next year, the number of predators will grow because they have a lot of food. And then the predators would eat all the mosquitoes next year and the number will drop. And then again, there will be few mosquitoes. The predators don't have enough food, so they have to wait the cycle of the mosquitoes to grow, and then the predator number grows again. Then they eat them up, and then it drops again. So you get these oscillatory orbits. If the growth factor goes even higher, then you get chaos. Then you get unpredictability, really. Okay? So that's one thing to note. If you're looking at these numbers and you see the equation, if it's a clear growth factor, it's a multiplier. If the multiplier is larger than 1, you know, well, it's bound to grow. If it's much larger than 1, you're thinking it might start to oscillate. If it's even higher, you're thinking I'm likely to get chaos, noisy stuff. Okay? Cool. I think that's that. So you guys go for it. And obviously I'll check your bits and see how fun it gets. Cool? Wicked. Nice introduction, a full hour. Bloody hell. Continue. Hello. So let's do some enveloping together. So in fact, what I'll do then is I'll try to produce this type of synth myself. Okay. So how does this work? Well, actually, at this stage, I will also use variables to make it clear. So I will have 3 envelopes, and the way the envelopes work is that the envgen is the wrapper, and the first argument is an envelope that is being essentially prepared. So actually that's the one thing that you see here, which would be the kind of this next step, that if you want to change the parameters of the envelope, the only way you can do it is by level scaling, level biasing, and time scaling. Because that's the point about these envelopes, that they're prepared to be really efficient and that they can run, but you cannot change the numbers, the parameters directly, because they're already embedded into the running envelope algorithm. So that's what the env does, but you can scale the time, means stretch or compress in time. You can scale the level, so you can make the output range larger and smaller, and you can do the level bias, which is the offset of the level. So those will be the ways that you can actually make it so that every time you rerun the envelope, it is slightly different. Okay, so here it gives me the options. I'm not sure what I'm really interested in. Let's do a lot of ASRs. That's fun. Okay, attack time, I'm not sure, 1. Sustain level should be, who cares, 0.5. Release time, let's have 5. Okay, so this is my envelope, and then I need a gate. Okay, so I will definitely need a signal that will trigger it. If I have a gate set at 1, it will run once. Okay, so let's for now just do that, and then we'll do the next bit. So this is my A envelope. I'll create a B envelope. A envelope. This will be a B envelope and a C envelope. So what I'll do then is I'll just make them slightly different. This one, well, they should all be 6 seconds. Okay, so they match like that. So I will take this one to be 2 and 3, and this one to be 0 and 6. So the C will be my percussive envelope, because it starts, well, I can start it at 1 as well. It starts immediately at 1, and it drops down to 0 in 6 seconds. These ones start at, well, I think they start at 0, go to 0.5, and drop back again. So those are the values that will come out of these envelopes. Now, if this is not clear, it's always useful to plot these things, or just poll them. So if I run this, you see what is happening to this envelope. So it ran to 0.5, it's still at 0.5. I mean, the sound is unrelated at this stage. And then hopefully, some point it will drop back, I would expect. Not quite. 1, 2, 3, 4, 5. I think we are past the 6 seconds. Let's try this again. Okay. So it goes up to 5, but it seems to stick to 5. ASR. Yeah, it's a sustained envelope, so it does need a trigger that goes to 0, yeah? Shall we do something else then? Just for the sake of simplicity. Percussive envelope. What are the parameters here? Percussive envelope. Attack time, release time. That's more like it. So this one was, let's call it 3, 3 level. 3, 2. So essentially it's just the other way around. Okay, 0.1. Who knows? And then here I had 0.6. Let's go up to 2. Okay, so now I expect them to drop back as well. So it goes up to, this one should go up to, what did it go to 3, and it dropped back to 0, okay? So that's always very useful, you know, so you actually see the values coming out of the UGen if there is no sound, if things are not happening. You know, you can actually pull the values of the UGen. Okay, so I have these 3 envelopes. Please do not make these sounds at this stage. Okay, and then the Hanon itself, well, it has the sampling rate thingy, which is kind of dropping here. So I'm not going to drop it anymore. I'm just going to keep it at 3,000, maybe 300. Let's get some bassier sounds. And then I have the further parameters, which is the A. We can keep this in one row. A and B. These are my chaotic parameters. I won't be bothered with the starting values now. And then I multiply it with the C. Okay, so the C should go up to 1. 1. This is this. Am I saying this right? ASR, let me double check. So it was, it doesn't even tell me. So it was attack, release, and sustain level, yeah? ASR, attack, sustain, and release. Okay, so sustain level is the middle one. So I wanted to sustain at 1 and release in 6. So actually I've done this for nothing, because the 2 outer ones should add up to 6. Okay. Oh, command line failed. What am I doing here? Yes, this is unnecessary. Okay. There we go. Okay, so that's essentially it. Okay, that's the structure of this patch here. So I have 3 envelopes. 2 of them control the oscillator, the generator, and 1 of them is an amplitude envelope. Okay, and then the next thing would be to actually get these to re-trigger. Okay, so what I'll do is I'll produce a T signal, which will be my trigger signal. Now, in terms of the trigger, what you get is that if you are, every signal can be a trigger signal. So essentially, when a UGen expects a trigger signal, it will look at it in a specific way. But you can, you know, my voice can be a trigger signal, anything that I imagine can be. And the triggers are derived from non-positive to positive transitions. So essentially, in other words, crossing the 0 line from below. Okay, can you tell me how is trigger defined?
Defined?
Yeah. How do we define a trigger in a UGen? I'm just asking you because I know you're not paying attention and you're working on something else, and I don't know why. It's really out of place. Okay? So the trigger is non-positive to positive transition. In other words, crossing the 0 line from below. So whichever signal you input here for the envelopes into the gate parameter, it will derive a trigger from this. Okay? So, what you've seen already is the impulse generator acting as a trigger. So we can do this. Let's do... Well, these are supposedly 6 seconds of duration, but that's a kind of a long time to wait, I think. So let's make it every 3 seconds. Let's just re-trigger them. Okay, and then you can put this impulse here into the gate parameter. So this becomes my trigger signal, and then from this, if it didn't blow up, it did sound like it did blow up. It did blow up. Yeah, that's the proof that it was like stuck somewhere. So, but that's funny because without this, it didn't quite blow up, because this is by default 1. That's very peculiar. Ah, yeah, it does blow up in the end. Okay, so what I can do then is play with it. So from what I've told you, can you think of any way of trying to make it not blow up? So what are the sensitive values for the parameters? 0 is very sensitive. So what I can do is try to make sure that they don't go to 0. How do I do that in the easy way? Well, that's your range conversion, right? So what is the range of this envelope here? We've just looked at it with the poll as well. So the parameters were attack time, they're still there, attack time, sustain level, release time. So this envelope will go from 0 to the sustain level and back to 0. Okay? So how do I change the range such that it does not contain a 0? Afterwards, because you see, whatever I do with these parameters here in the envelope itself, it will go from 0 to the given number, the one in the middle, and back to 0. So that's something I cannot change at this stage. But once I have this signal, I can do everything I imagine, right? I can do all the arithmetic maths, whatever. So what's a good way? If I multiply it by 10, what will happen to the range?
0 to 30.
Very good. But I want to avoid 0. So I add, exactly. So let's try that. Let me add here 0.4. Let me add here 1.1. What's going to happen? You see? So it actually already didn't blow up like that. I'm actually finding that it could probably be much weirder. Let's get these envelopes to run much higher. Maybe not. So that's a bit of a game playing that you can try. I mean, I can try minus. Who knows? Probably gonna... Cool. Well, actually what I can say is that the first transition is really, really very quick. So I can try to decrease the ranges here. It still goes very quickly. Does that Still like that. You see, so I'm just making sure that the envelope runs a bit slower, and it does something like that. Okay, so now that it doesn't blow up, let's see if I can re-trigger it. Impulse KR every 2 seconds. Wow. U-Bahn. Okay, so what the hell is going on? And this is actually the crucial thing. If you understand why am I hearing what I hear now, because I imagine that you also expected to hear the same beginning repeat, but it doesn't happen. Why not?
It doesn't trigger.
It triggers. Well, you hear it. It's repeating at 2 hertz, but I'm never getting the sound that I started from. And that's the cool thing, because that's the chaotic orbit, right? So you remember that depending on where I start, I will run a different orbit. So the envelopes are re-triggering, the envelopes are running the same thing, but when I re-trigger the envelope for the first time, it already is going to be different because it's starting from a different spot. Make sense? So actually I would have to reset the whole generator in order to get back to the first sound. Let's see what happens if I do it at a very fast rate. Now it actually does reset. Goes back to the beginning. Okay, and then the final thing I'd like to show you is how you can manipulate these envelopes once they're running. Okay, so I cannot put an LFO to replace these numbers. Right, that should be clear, because this env definition does not run in real time. So putting LFOs there don't work. What I can do instead is I can create a level scale, a level bias, and a time scale. So I will have the same shape of the envelope, but I can stretch it up and down like that. So what I'll do here is I'll introduce some noise, which is essentially randomness. So I'll go for LF noise. I'll go for a fairly slow change. Okay, and multiply, add, I think I'll leave it like that. Let's see if that does something. Now, I will do it for each one at some point. See, I've lost it already, it seems. Oh, I probably turned down the volume, that doesn't help. Okay, it's still doing something. I'm not a huge fan of how it sounds at this stage, but obviously we're just testing it. Let's get it to go a bit faster. And now it's okay. How cool is that? Moderately. So just to make it extremely cool for the end, let me show you a little technique. So what I will do here is I will fill an array of 10 of these. And I will call this R. So if I do this, what happens is that it will multiply everything 10 times. This synthesis structure will be repeated 10 times, and each one will be a separate element in a list. So if I run this, what do you expect? Well, actually, it's plugged in incorrectly. For now, I had only a single signal as an output, which was always on the left speaker. So if I do this, I'm actually sending out 10 signals in a list. So what I will get is left and right, and the rest won't be audible. I mean, if I had a sound card with 10 outputs, then I would actually get one of these on each output. And because they have this randomness in there, each one would be slightly different and start changing differently. Okay, now I don't have that. So let's hear the stereo version, hopefully. Play as, what did I do here wrong? Yes, I need another bracket. Is that one gone then? Oh no, I'm just... So you see, they have the same initial period, but because of the randomness, they're doing slightly different things. And then what I can do is I can sum that. Okay, sum is something you can do to every list, and it does sum every element. So now we'll be back to one speaker, but I will have 10 of these running at the same time. So what I should probably do is lower the volume, just so we don't distort horribly. Okay, and because I'm a bit bored of this 300 Hertz, I'm gonna make it a random value between 300 and 600, such that each oscillator... There we go. Maybe it's a bit of a large range. Let's try to get them closer in. That's my new piece. There was, by the way, the Twitter SuperCollider challenge. They made a CD of it, and there was huge. I think what was it, 147 characters. So actually, the challenge was to make a full piece of electronic music in SuperCollider with 147 characters, and the submissions were like, wow. You know, because that's the power of SuperCollider. I mean, this, you know, it's a neat trick, you know, just to get things going. And there's millions of neat tricks. So these guys were really up for it. I think it's probably still online somewhere. You can trace this. Cool. So that's it for today, guys, or for this week, I should say. And we shall continue next week. All good?